This is another topic, and it really depends on which field you end up working in, whether you work with these every day or you never see them again. Could be that way, just depending on what you do. So this week, we're going to focus some energy on geometric dimensioning and tolerancing. So by this point, we've got a pretty good understanding of the word tolerance, right? What does tolerance mean? Yeah, it's how much allowance we can live with, right? How much deviation from exactly what I'm saying it needs to be that I can accept, right? A tolerance, allowable amount of variation. Tolerance. If it's within tolerance, it's okay, right? If it's outside of tolerance, it's bad. I can't use it. So when we talked about tolerances up to this point, particularly last week, we were trying to figure out these maximum shaft diameters, minimum shaft diameters. So we'd have a limits tolerance with the max over the min, and the tolerance was the difference between those numbers. And it had to do with the physical measurement at a precise spot, right? The diameter of that shaft or the diameter of that hole. What we're trying to do with geometric tolerancing is control not only the size of those features, but also the shape and form of it. So, I think as we go through some of these examples, it'll make a little bit more sense. But we're still talking about tolerance, which is the amount of allowable deviation. But we need things to have not only the right size, but also the right form or shape. If I'm talking about a shaft, it needs to be straight within a certain amount of tolerance, as well as the diameter have a certain tolerance on it. So, we're talking about form. Or relation, we'll kind of get into that. But just some general terms that you might run into, you probably will see them on the exams and stuff for the chapters. A basic dimension is just that numerical value that we use to describe the theoretical exact size. In technical drawings, a basic dimension is actually, theoretically the exact size. So that variation is part of this geometric dimensioning and tolerances. And a lot of times these basic dimensions, I don't want you to think of them as like all the dimensions that we've been doing this far are basic, but this has to do a lot with positional tolerance dimensions. They're basic. You'll see these with a rectangle around the number. So it'll be a regular dimension like you've seen, but the number will have a rectangle around it. So that's going to be a basic dimension. And it falls mostly on this next one, true position. So that's the theoretical exact position or location of a feature, whether that feature is a hole or a protrusion or something like that. We're locating the position of it with a basic dimension, and it's a true position, theoretical exact spot. The deviations are measured from there. A datum, for the most part, we're going to think of it as a plane. So a face or a plane. You guys are starting your inventor class, and you start a sketch on, the XY plane or the XZ plane, and so you're measuring things like that. But a datum is just a reference plane that I'm measuring from. So like most things that we've done so far, if I'm going to have datums identified, we start with datum A, B, C, D, so on and so forth. So they're identified with letters. And we'll see some examples. We could have a target that's identified as a datum, and it's got a little different symbol. And then we have datum features, which could be a shaft or a hole or something. Now that is a datum, which means it's something it's being measured from. It's a reference for a measurement. Okay. So another term that I kind of want you to understand is this virtual condition. And this is the whole thing that we're trying to do with this geometric dimensioning and tolerancing is virtual condition, which is the worst case scenario that's still acceptable. Okay. So in this example, we've got this round bar, think of it as like a shaft. And it can't have any more than 0.06. It has to be straight within 0.06. So the axis running through the center of that shaft the entire length of that shaft has to stay within that 0.06 cone or cylinder, not a cone, but a cylinder. You know, and you can see the extreme that the shape could be there. You know, it's quite, you know, it's quite contorted, but it's still okay as long as it's within that amount. But any more than that, then it's not going to fit with the part that it needs to mate with. It just simply won't go together. And that's what we're trying to do is ensure that all of our parts fit together. Where you see geometric dimensioning and tolerancing primarily are on the fabrication of jigs and fixtures used in production. So we're making these tools with probably 4 times the precision that we expect to get on our output parts, so that, you know, all the parts we make with these tools fall within tolerances. So we're really controlling the shape and size of these jigs and fixtures so that I can accurately control the shape and size of my output products. So it's a tooling is where you see this a lot. I mentioned earlier that I did the blueprint reading class for Danfoss up at Cersei, and they use a lot of geometric dimensioning and tolerances on their hydraulic valve bodies. So they're really trying to control the shape of all these little intricate pieces going together. This virtual condition is like the extreme scenario of what this would look like in that specification. So some other operators of geometric dimensioning and tolerancing include maximal material condition, which, just like the name says, maximum material condition. I want you to think of that as if I had a part, and I'm talking about, you know, the outside diameter of a shaft, then the maximum material, how heavy that shaft is going to happen when that shaft diameter tolerance is it going to be the minimum or the maximum? It's going to be the largest it can be, right? So that part will be heavier when that shaft diameter is on the upper side or the upper limit of its tolerance, right? What if I've got a part with a hole in it, and the hole is at, in that part, that now we're talking maximum material condition. It'd be the minimum hole that makes maximum material condition. So I want you to think of it like the mass of a part instead of, you know, just whether it's the max limit or the min limit. How heavy is the part? The same thing holds true with least material condition. So what this means is I'm given as tolerance, but that tolerance is only being applied when we're at maximum material condition or we're at least material condition. If we're seeing these operators, and these symbols look like the letter M in a circle and the letter L in a circle. That's the symbol for those modifiers. If there's not either a M or an L, then the tolerance is being applied regardless of feature size. So here's an example of what I'm trying to say with that, regardless of feature size. So here we've got this shaft on the left. We see the small shaft. It has a diameter that ranges from 0.605 to 0.615, and the shaft has got this straightness tolerance. That's what that little box there with the straight line in it and diameter 0.015. That's called your feature control frame. That's actually where you put these geometric dimensioning and tolerances. So this is saying that shaft has to stay that's straight within 0.015. So if you look to the center illustration there, you see the pink cylinder that has that 0.015 tolerance zone. And the center of that shaft, regardless of what the diameter is, has to stay within that zone to be within tolerance. And so now if we think about, how much, what the actual tolerance amount is throughout that entire tolerance range, the table there, we've got the lower limit of the diameter 0.605 all the way up to the upper limit at the top of the chart, 6.115. And the tolerance zone is the same 0.015, regardless of where that shaft actually measures within that tolerance zone. Does that kind of make sense? If it were maximum material, then we would only apply it at the maximum limit there. And we'll see another slide, I think, where that's shown. But right now, regardless of feature size, means that same tolerance amount is applied to that shaft regardless of what the diameter actually measures, as long as it's within our specs. You know, if it's outside the diameter tolerance specs, then it's outside the geometric dimension specs too. It's just out of spec. So I'm not expecting us to leave here being geometric dimension and tolerances, but there are some things that I think you should go away from here realizing. And the big things for me are that you realize that some geometric tolerancing are for individual features. Okay. The straightness of a shaft is just, you know, how straight is this shaft? The flatness of a surface is just how flat is this surface? The circularity of this shaft or the cylindricity of this shoulder on a shaft, you know, those are only related to themselves. They're individual. And then if you look down at the bottom there, you see related features. So, you know, in particular, if you think of perpendicular or parallelism, well, this feature that I'm saying to be perpendicular has to be perpendicular to something, right? So it's related to something. It has to be parallel to something, right? It has to be measured within this angular tolerance to something. It's a related type of tolerance. Okay.
Looks like constraints.
It is. It's the same kind of thing as the constraints. They're the same symbols, very similar to what you see. That's really what I'd like for you to leave here, having a basic understanding of if something is an individual feature and if something is a related feature. If it's a related feature, then I know I have to specify what's it related to. And the thing that it's going to be related to in every case is going to be a datum. Okay. So now we're saying we're parallel to this datum, or we're perpendicular to this datum, or we're within an angle of this datum. Here's the feature control frame. And AutoCAD's got it'll make the feature control frame. It'll put the symbol in there, you can put the tolerance in there, and it'll put the box, you know, lines in the box. It'll make all this part of it. It does not put an arrow on it. So you have to manually put a multi-leader, put an arrow, and attach it when you need an arrow. Inventor has a great GDT tool. It puts an arrow and does everything. So hopefully you're about to get your inventor legs under you. I normally have people drawing about the third week. So I'll do a chapter a week. I think that's in the third chapter. So I don't know what you are waiting on. But
School to start back.
yeah, I guess so.
That's the week.
Yeah, true. They missed that whole week. So that's not going to help us out any. AutoCAD's got a feature control frame. It's on the annotate ribbon. Actually, it's in the dimensioning tools. So we'll look at that here in a second. So here's the feature control for a related item. So we have, you know, it's angular. So we have to say angular to what? So now we have angular, we have the tolerance 0.5, and then we have angular to what? A, okay? So that's a datum. That A in that square is a datum. And if we look down below, straightness. So straightness is an individual feature, all right? And if you don't know, you can always look back at the table and it'll tell you. So straightness is an individual feature. That axis has to be straight within that diameter cylinder of 0.15. And in this case, we've got the modifier maximum material condition. So again, the AutoCAD tool put that box together for you, put all that in there nice and neat. You'll have to make a leader for it. So form tolerances, these are form tolerances for individual features. So they're not related. So when you use these symbols, you will not include a datum in the feature control frame box. So we have straightness, flatness, circularity, and cylindricity. That's a hard one for me to say too. I probably didn't even hit this very good, but that's going to be the actual size, right? If we actually measure it, it's what it actually is. Not a nominal size, not a basic size. It's what it really is. It's actual size. All right, so here's some examples of how we might see these geometric dimensioning and tolerances in a drawing. So we've got this this front view and the side view, and this drawing is going to have all your regular dimensions on it too. So just because they're not here doesn't mean yours won't have them. You'll have all the regular stuff that we've had all along. But now we're saying we've got this is a datum identifier. So this is saying this extension line is coming off this bottom here, which what does that mean? That means this bottom face, this whole plane that's represented by that face is datum A, right? And this B is coming off this extension line from this back side. So that whole back face, or it's actually a plane, goes to infinity, both directions. But it's represented by that face is datum B. So, we start with A for the primary datum, B for the secondary datum, C for the tertiary datum, and so on and so forth. That Danfoss stuff had crazy number datums. So you'll see it depending on what you do. So what we're saying here is that, this 30 is a basic dimension. It's in the square. This angled face here has to be within 0.002 degrees of A and B. So it's got to be lined up with both of those faces. Then that tolerance amount. So it's on the 30-degree angle from A, but it's within 90 degrees on B, right? Does that kind of make sense? So we've got, from A go to 29.998 or up to 30.002, and then measuring from the B, that face has to be within 90.002 or 89.998. Does that kind of make sense? And then we have the flatness. So the flatness just means all the little irregularities on that surface cannot exceed 0.001. So we've got two virtual zones over here on the right. We've got the 0.002 angular tolerance. So that whole face has to stay within those two lines. And then we've got the smaller 0.001 flatness tolerance, where all the irregularities have to stay in that face. Two different specifications. Flatness is individual, angular is related. So circularity has to do with the all the points on the outside edge are the same distance from the axis. So has anybody ever made a part like on a lathe? Anybody ever turned a part on a lathe?
Isn't that like similar to like a lathe? It like carves out the metal around a part.
Yeah. Yeah. So, a lathe is most cases horizontal. The material is turning and a cutting tool engages it, and table legs, stuff like that, yeah. Wood lathes. But the circularity, when you set up your part, you try to get your stock in your lathe, running straight. So machinists have always got a dial indicator and a magnetic base, and they'll put that dial indicator on their part when they put their stock in the chuck, and they'll rotate that stock or that chuck until that dial indicator is not moving anywhere. So they're trying to get that running as true and straight before they make their part, so that their part comes out right. So they're measuring circularity of where that dial indicator is touching, and that sets that part up to run correctly. Cylindricity is very similar, but it has to do with the circularity is kind of like at a spot, and cylindricity is the entire length. And you can see those virtual. And this is really this helps me kind of better understand what is it we're really trying to do with this. Well, we're trying to prevent some of these common irregularities that causes parts not to fit together right. Even though we may measure the diameters and they be the right size or within our tolerance, if the shape is not right, they don't work in our application. So we're trying to control not only the size of things, but the shape or form of the features themselves. So you might have, ovality or lobing or just random irregularities that cause these shafts not to go in these holes. And, if you could picture a really deep hole that has a long shaft going into it, that shaft has to maintain its straightness pretty well, or you're going to kind of get in a bind going down, right? So we've talked about datums. That's the theoretical, and for the most part for us, we're going to use datums as planes or surfaces or faces. We're not going to do a whole lot with datum features, I don't think. But here's kind of how the datums lay out. So we've got that primary datum, in this case, along the bottom surface. Secondary datum, datum B, is on the back face. And then we got datum C on the side. They don't always have to be top, back, side like that. This is just an example. If you have another datum, it would be datum D, E, F, so on and so forth.
They all have weird names to them too.
Probably.
Like C, what, how do you say C?
Yeah, I don't even know if I can say I said it a while ago.
You did.
Didn't fumble. I don't think I can do it again. Yeah. Datum C is what we're going to call it. Yeah, I said it a while ago. I was proud of myself, and now you're calling me out on it. Think about it too much, I won't be able to say it. Here's how we identify these datums. We're going to use the ASME symbol at the bottom, and we're going to use the solid field triangle. One of them, the one on the left's got a hollow triangle, the one on the right, solid field. AutoCAD does not have, a datum identifier tool, so we'll have to make that just like we did our little surface texture tool. If it's not already there, I'll make sure that we have this in the course stuff with the cutting lines and all the other stuff. But AutoCAD will put the box with an A in it, but it won't do the rest of it. So we'll have to manually do that. So that term of the condition for which all the surface elements are all in one plane. Flatness. So these are some of those related, right? The orientation, angular dimensions exist between, at least two features, right? So we have to say we're angular relation to what? Datum A or datum B or datum A and B. The condition of a surface or axis is specified angle other than 90 degrees from a datum plane or axis. So perpendicularity is that 90-degree angle, and parallel means they're on the same angle. Okay, I put the symbols in there. You won't have to draw the symbols like that. But so here we've got, a hole. So this is one way that you can apply your feature control frame to your dimensions. Here we've got a hole, 10 diameter up to 10.022, that is parallel with a diameter 0.05 at maximum material condition. So the hole at maximum material condition is at 10.0 or 10.022. Yes, that would make that part weigh the most, right? So the lower limit of the hole is maximum materials when it comes to holes. And that is parallel with datum A. Now we can't see datum A. It's not the same as what you're seeing on the right. It's a different part altogether. We can't see datum A on this example, which is a shame, but that is how you could apply a tolerance to a hole. You can hang that feature control frame right underneath that dimension, and that's applying that to that hole. Over there on the right, now we've got a shaft. And the shaft has got the 19958 to 1998 tolerance on it, and it's saying that it has an angular GDT must be within 0.15 of datum A. So we got to be at that 80.15 or 79.85 tolerance with datum A, that measurement. This one doesn't have a modifier, but if it had a maximum material modifier, it would be the larger diameter in this case. It doesn't have that though. So similar examples, I think, the parts that we're going to do are pretty simple and straightforward. So I think you can kind of look back at these examples that are in your book to help you figure out where to put the feature control frames, how to hang them in place. And I think we kind of hit it all, but let's see if there's something else I'd like to. I think I've got some. Got some maximum material. I don't guess I did. Let's look at the problems that we have for this week. Book 7.6. Let's see if I can open it. So it's a pretty straightforward drawing, I guess. We've got this shaft, and I believe the shaft has got us a tolerance of cylindricity, 0.002. So there wasn't much to that. We've got a length tolerance that we're applying, got a diameter tolerance, and that. So if you look at this in the book, maybe I should just go get my book. I think I will. Go grab my book. So if we look at 7.6, it's on 7-23 of your book. It's going to end up looking like this. You're going to include all your general notes and stuff that you've been putting in it. But basically it says, we're going to add a cylindricity tolerance of 2/10,000ths. And we're going to make the length of the pin 4 with the plus 0.005, plus 0.01 limits. So we've got that. And I recommend when you make these parts with tolerances that you just pick one and make it that length. And then you only have to adjust it one way instead of having to, instead of putting 2 adjustments in there. It just makes it easier. Pick one limit and then adjust it the other way down or up. Same way with the diameter. We've got the diameter limits that's given to us there in the drawing. And then we need to add the feature control frame. So to put a feature control frame in, we've got to go to the annotate ribbon, and you got to drop this little dimensions guide down. And the feature control frame is this guy right there. So when you click on that, you'll get this kind of tool. So the very first box is whatever your symbol is. Straightness, flatness, cylindricity in this case. And then we put our tolerance amount. If you had a diameter symbol, you could pick that there. You got maximum material, least material conditions there. Tolerance, cylindricity is an individual tolerance, so there's no datum A, but if there were a datum, you would put the datum letter in datum 1, 2, or 3. If you had to go out further, you just have to manually do that, I guess. But when you pick OK, that'll pop that box in. In this case, we can just drop it right there by the diameter, and it understand. Everyone should understand what that's talking about. So the other problem is 7-7, and again, we've got some general tolerances given to us, and then we're going to add a feature control frame that specifies parallelism of the upper to the lower surface. So that means the lower surface is going to be datum A, and the upper surface is going to be parallel to datum A. Now there's not dimensions given for that step, and I think in the assignments I probably give some insight there. So complete the drawing 7-7. Dimension the notch to work with the given instructions. So, I don't really care what your size of your notch is, but it needs dimensions on it. And then just kind of work your way through those exercises. They're really not that, there's not much to those first several. I think I may have, so 7.6 through 7.9 are right out of the back of the chapter 7 in the textbook. 16.26 is one y'all are going to love from me, but we are actually going to create this drawing. It's not that bad. I've got the drawing given to you. I've got all the dimensions there for you. I've got all the new geometric dimensioning and tolerancing and stuff that you need to include on there. So I want you to put all that in place. And then all the stuff that's red, I want you to explain to me what it means in your own words. Just put a little note right there by it and type what it means in your own words, each little red thing. Does that make sense? You don't have to include these notes here. But the drawing views, GDT stuff, dimensions, surface texture stuff, what does all that mean? So you got, handful of really easy, quick stuff, and then you got one that might take you a little while. Open book, chapter 7 exam, of course. Make sure you use your book. And this right here is what we talked about last week. So it's just same stuff. Questions? All right, then. Well, I'm going to shut it off and let y'all get to it.